Friday afternoon, in person and on Zoom. So today we'll have Lawal, but before she presents, I feel like I should introduce myself because I think very few people know me here or on Zoom. My name is Maria Bakhtiarova. I'm also, just like our speaker, a postdoctoral scholar here at Berkeley, working with Dr. Rodriguez on the Urban Health in Latin America project. So today we'll hear a presentation from Lawal, who is currently an American Society for Engineering Education postdoctoral engineering fellow here at the Civil and Environmental Engineering Department at Berkeley. She received her master's and doctoral degrees from Georgia Tech, and her research interests lie in applying fine-scale air quality modeling and mathematical methods to urban systems and processes to understand the overall impact and compounded effect of city infrastructure and new technologies on urban air quality, sustainability, and inequity. So the seminar will be about 35 to 40 minutes, and then we'll have time for questions. Thank you so much, and join me in welcoming Dr.
Thank you so much for that wonderful introduction. Hi, everybody. My name's Abby, and like Maria just talked about, I will be looking at explaining my research, which is anthropogenic emissions and their interaction with specific urban infrastructures. So just a little bit of history about me, following in her path. My path to environmental engineering, I started out with a chemical engineering background, and then I worked in industry, doing energy balance equations around the refinery, troubleshooting projects. And then I decided, well, let me go back to grad school. While I was working, I didn't want to lose the money, but while I was working and take some classes. So one of the elective classes I took was an environmental engineering class. It was water chemistry, and I was hooked. There was no going back. So I switched over and went to grad school to get a degree in environmental engineering. And that brings me here, my trajectory here as a CEE postdoc, working for Dr. Ivy in the ACMEL lab, where we do air pollution modeling. So air pollution modeling is we do interdisciplinary work, and we integrate data analytics, we integrate observational data, satellites, and I'll discuss more about that in the projects you'll see. So for those in the crowd who don't know, my lab mates are there, but we use CMAC, which is our computational air model. It takes into account emissions, kinetics, photochemistry, basically atmospheric dynamics. And then basically what we do is you take those inputs, and then the air quality model takes into account these engineering equations. You have your mass balance, momentum. Thankfully, we don't have to solve these days, but it's all in the computational model, and the atmosphere is modeled like a box grid. So all these equations are solved simultaneously in one grid, and then it transfers to the next grid simultaneously. And if you do parallel computing, any computer scientists here, you can split this grid into solving these separate boxes or columns, and that will speed up the computational time. So that's what we do mainly in the ACMEL lab. And then the output, you get like a simulated air quality field. This is like over the US. CMAC is what you call a regional model because it models over the United States primarily. And then you get your air quality, your simulated concentrations. And then you have your satellites, which you can combine the observations with. So my interests are in urban systems modeling. This is how I use air quality, what I use air quality models to explore. And we know that anthropogenic emissions have adverse impacts on human health, the climate, and global ecosystems. But the sources of these emissions and the degree to which they're emitted, they are largely affected by the infrastructure segments in urban areas. You get your power supply, of course, your transportation, and of course, your socio-economic demographics. So cities are hotbeds. Why do I look at cities? Because cities are hotbeds for these sources, because most of the infrastructure segments are in these cities, and they are highly integrated and combined with large populations. And they consume a lot of the bulk of the global energy use is driven by cities. And then some of these emissions, they're not always equitable. like, look at this. This is a map of Atlanta, Georgia, one of the most ninth largest metropolitan areas in the U.S. And you can see, like, the top right, the upper columns, that's concentrations of particulate matter on the left, and I think NOx on the right. I might have that backwards, but those are the concentrations. And you can see anywhere that's in red, that's more pollution. And who happens to be living in those demographic areas? Anything with a plus is a highly diverse census tract, which is largely consists of African Americans. So basically, you can see the emissions of these cities is not equitable. Most of the vulnerable communities are exposed to higher levels of these pollutants. And then look at the health prevalences. Anything that's a darker shade means that that community is prone to higher prevalence of like coronary heart disease or asthma and things like that. So when we're looking at cities, we have to consider the future. How many people know in 2050 what's the population going to be? Anybody can take a guess? Okay, right now it's, I think, 7.6 billion. By 2050, it's going to be 11.6 billion. Woo! Yeah, no, it's going to be really, really a lot of people living in condensed cities. And that's going to have an impact. And we need to consider, how are we going to project with these increased populations, increased demand, while making the cities equitable, and also considering the emissions and their sources. And then we need to consider, if we're going to design these kind of cities, we have to take into account policy, we have to take into account, of course, the demographics, the economics, because who can afford what, and the technological changes. So to look at cities, because it's very complicated, well, my main focus is air quality and health. And a city can be looked at as a subsystem. That's why I call it urban systems modeling, where you have the different components that go into a city. And, you know, all of these interact synergistically, non-linearly, linearly. You know, there's so many ways these systems can interact with each other. So how do you delineate these things and determine what the policy or what the effective measure should be? So this is something I propose in my graduate work, like, okay, there's so many frameworks in which to analyze these specific segments, but I decided to come with a circular framework because this does not presuppose a particular path. It doesn't say, first of all, you have land development, and then you have population growth, and then you have emissions. This just says these are the elements of what the big areas of what goes into the analysis of urban systems, and then you can look at how do they interact. So it kind of doesn't tie you to a method of thinking about it linearly per se. So I'm going to show kind of how I use this framework to think about the urban modeling results that I worked on in grad school. So I'll just go into it right now. The first thing with air quality is you have to consider what are the regulations. By the Senate passes the laws, and then the EPA determines what is the best way to enforce these laws. You have the Clean Air Act, you have the NAAQS, and you have air monitors that are there to enforce these things. So in doing air quality, we want to look at what is the impact of air control regulations on air quality and equity. So, you know, these are the systems that I showed you in that previous chart. So when we look at government, because that has to do with policy, what is their role in regard to particulate matter regulation? So with particulate matter, you know, it's ultra fines. They're detrimental to human health as well as the environment. And they also have climate effects such as radiative forcing. And of course, the health measures are one of the primary reasons why particulate matter is of great importance to public health, because it comes from emissions and it can create asthma, a bunch of respiratory diseases. So the impact of regulation so far, it seems to have been effective. We can see over the past decades, NOx, CO have come down, and also you can see SO2 emissions have come down. And if you look at the chart over the United States, for the most part, all the emissions have seen reductions except red here. Anybody can hazard a guess why this is higher? Oh, please. What do you say? Yes, wildfires, exactly, the burning. So that's why you see higher particulate matter. But overall, the regulations have had a good effect on the rest of the country. So, and you can also see SO2 emissions as measured, they have been coming down. But we need to say, what about aerosol acidity? So the reason why aerosol acidity is important, first of all, it comes from the sulfate and the NOx emissions that are coming from these sources, and they form into the particular the aerosol phase here, and then that's what gives the aerosol its acidity. Now, the acidity can be bad because, first of all, it can increase the solubility of metals, which can impact, oxidative stress, which leads to health effects. And also the pH can change the aerosol chemistry and lead to more SOA formation, secondary organic aerosols. So that's why it's an important parameter. So if emissions are going down, that should mean SO2, sulfate, and nitrate should be going down. So shouldn't the pH be going down as well? What about the pH? So we looked at studies, sites over the US to just see if the reduction of emissions corresponded to a reduction in pH. We just used two general methods. We used an air quality model, and we used a thermodynamic model. And we divided the sites into 5 main key areas over the US, which I'll focus on for this talk. And these are the results. So if you look at sulfate is trending down. Now, this data is coming from monitors, so we're not modeling this. So this is a measurement. So this is good data. So you can see the sulfate is going down there, but what you do not see is any noticeable change in the pH. It pretty much is statistically, there's no change. You see ammonium, which tends to track with sulfate, but nitrate, you don't see any change. And there are different reasons why you don't see much change in nitrate, because nitrate usually forms when the pH is higher, and when you have sulfate, the pH is low. So you don't see much change in nitrate. And then when you use the CMAQ modeling results, you don't see any decadal change between winter and 2011. And what are the implications of this? The areas where you have highly populated areas, which happen to be diverse and happen to have the most pollution, these places are more than likely seeing particulate matter with low pH, which is probably could be correlated to the diseases that those tracts are seeing. So when you consider government policy, you also have to consider population and demographics. You have to consider the climate. That's what this framework shows you. These are the many areas you have to consider. And a few highlights of this study show that, despite reductions in sulfate, it's very little impact on aerosol acidity. And we may not see a change in aerosol acidity for decades to come until sulfate is much lower. So you see, this is how policy affects your air quality. And sometimes you can do policy, but you still don't see the change in the environment. So one has to be very careful about the changes we make to the environment, because you may not be able to reverse man-made effects. So now we get into transportation, and I'm going to talk to you about an airport, a study that I did on an airport, which is related to, of course, the emissions. And that's why I highlight transportation here. I notice transportation falls under land use, but transportation also falls under technology. That's the beauty of this framework. You can put these buckets in any circle you want. So what is the background on airports? So we do know they contribute to ground level pollution, ozone formation, but we do know, I traveled just this week, and the demand for airport travel is beyond anything I've observed in the past. So airport demand is going to continue to, air travel is going to continue to increase, and most of these airports are located next to major downtown areas. And why is that important? Because these areas are highly densely populated, and any emissions from airports will affect a greater amount of people associated with each city. So when, in the CMAQ modeling, and anybody who has any questions, feel free to ask me. But so when we take into account air quality modeling and we want to assess airport effects, we have to consider what are the emissions. With airports, there are two types. There's ground sources, everything that happens at the airport, that only accounts for 10%. And in the upper layers, the actual cruise, that accounts for 90%, occurs mainly above 1,000 meters, like you can see, mainly, and that's called LTO. But most regulatory modeling practices only consider the ground sources. Why? Because ozone is formed on the ground. So that's pretty much why they generally consider that. So they just consider just the ground sources. So what this project was going to do is we were going to consider an emission inventory that takes into account both the ground as well as the crew sources. And let's see what that difference looks like when we do the modeling in with CMAC. That's our model. And our hypothesis was, or is, that airport effects are underestimated with the default inventory, the default being just the ground source emissions. So this is the general setup. We focused on Atlanta. We looked at 1 month, 2019. If you model with CMAC, they will call it platform 2016. These platforms, they come out every 3 years or so. And then the chemical transport model, they're up to version 5.34 now, but at the time this was 5.32. And CB6, that's a chemical bond mechanism. That explains how the chemical reactions are treated in the model. And then the meteorology, we use WRF, which is weather research forecasting. Maria, you use this too? Do you use WRF, or what do you use for your meteorology?
Well, recently we've been using modeled data set from Euro 5.
Okay, I've heard of that. Yeah, okay, good. Yeah, so those are all similar WRF, meteorology models. We use WRF because it creates inputs into like a 3-dimensional grid box, just like that. And so anyway, so this is the modeling domain. You usually have to set up a modeling domain. And like I said, our overall goal was to evaluate 2 different airport inventories. And I'll just kind of do this crude estimation here. This is what the inventory looks like, the default. It's all on the ground. We basically generated a 3D model. And why is it squared? Because as the plane takes off, it's going off this way, it's going off that way. This is my animation version. I'm no artist, but anyway, but this is just the general idea. So the main thing we changed inputs were the emission inputs. Like I said, we just mainly changed the 3D inventory. And then we also evaluated those results using satellite observations, TROPOMI. Basically launched recently in 2019. And the reason, anyway, this is what it looks like when you combine satellite retrievals together with air quality model vertical profiles, you actually see the gradients of the emission sources. So this is the airport in the middle of that modeling domain, and these 2 are power plants. This is what the retrievals look like before you process them with CMAC, with air quality vertical profiles. So it's a conversion that takes place. And the results show that TROPOMI, it does capture the airport and other high emitting. Oh, I should qualify. The satellite reads various products and we're focused on NOx because airports emit high levels of NOx, NO2 and NO. So, and in this case, NO2 actually. So that's the airport. You can see right center just sticks out. And then this is what you compare with the CMAC computational model, which is based on ground inventories. That's what we call it in the modeling domain. And let's look at what ozone looks like in general. You can see this is the airport here. Ozone is generally high away from the airport, about 80 parts per billion. If you were to look at particulate matter number concentration, you can see it's very high. It kind of follows the airport and it also follows the roadways. You have a lot of diesel trucks. If you look at PM 2.5, which is formed by both secondary formation as well as primary emissions, you can see the airport. I mean, just a high emitter of PM 2.5, if I can find my mouse right there. And this is some of the site or plant. Now, if we contrast those results with the default emissions, which is used, by the way, for regulatory health effects, you can see so we take the new inventory and subtract it from the old inventory. So anything that is red means that the new inventory is estimating higher ozone. So you can see by using a more accurate representative inventory, you can see that we're actually seeing more ozone because of the airports, as high as almost 2 parts per billion, which is high, especially for 8-hour maximum ozone. Particle number concentration is a little different. You can see it's lower at the airport, but why? Because when we created that airport inventory, we had to dilute the emissions because we were allocating them vertically up. But the point here is that beyond the airport, you can see everywhere is elevated particulate matter. So that means that the impact of the airports can be felt beyond the airport itself, and you're going to see elevations beyond the airport. Same thing with PM 2.5. So conclusions. Airports' impacts are higher than we think for ozone. Airports and effects are not constrained to the airport. And because of this, airport effects could offset emission control gains, especially if demand continues to increase. So this is, when you consider this, you have to consider policy regulations as well as land use considering population demographics and consumer behavior and infrastructure. So last but not least, my favorite, well, my current topic, I'm looking at impact of electric self-driving vehicles on emissions and air quality in 2050. So I put transportation down here, and that's technology. I hope I'm doing okay on time. Okay, great. I might be talking like a speed demon, but apologize. Sorry, this didn't come right. But anyway, transportation is a significant component of emissions, energy consumption, significant component of energy consumption. You can see 28%, but it's also the largest contributor to urban pollution. Look at that, over 50% of NOx and CO. And this is figures from a paper that was published in Professor Russell's group, my thesis advisor. I'm looking at Atlanta again. This is the roadway infrastructure, and you can see, look at that. Look at where the heat signature of all these pollutants are, 2005. So this is what the transportation sector, it's high, they're elevated sources of pollution above other sources. Once again, we do know that regulations have been effective over the time, but when it comes to transportation, they've even been more so effective, 90% reduction in CO and PM 2.5. And by 2050, a car in 2050 that is run on pure gasoline is expected to be very, very clean when you contrast it with 2011. Pretty much, they're going to become quite clean. But there's another trend on the way. In addition to clean cars, more efficient gasoline cars, trends show that electric cars are on the way to replace gasoline cars. All the automobile makers are joining the race, and this is coming up in about, I think, 2030 or 5, I think so. But then the combination of automation and electric vehicles is affecting consumer choices. Like, first of all, you have autonomous vehicles. With autonomous vehicles, you're going to see an increased vehicle miles, VMTs. This is VMTs driven. That's because autonomous vehicles will allow for ride-share fleets. So you'll be able to see increased miles. You're going to increase access to people. So that's going to increase the number of miles driven because of the automation of electric vehicles. And increasing the access, so that basically increases the access for share rider fleets. But another thing is also driving the impact of electric vehicles is because you have the economic and energy nexus, gas prices. These are Bay Area prices in October 22nd. With these high prices, most people are going to be going to electric vehicles. I personally don't think if I live in California, I won't be buying a gasoline car again. But so with gas prices like these, who wouldn't want to adopt an electric vehicle? So what does all this mean? Given these trends with clean gasoline cars, electric cars, VMTs, this means by 2050, these are the passenger car fleets. Most of them will be some combination of an electric vehicle. You have battery electric vehicles, you have hybrid, you have plug-in hybrids, but you can see, look at the gasoline, which started out 90% at this trend line. By the time you get to 2050, it'll be down to 10%. So that's going to be the trend. And because you have electric vehicles, you're also going to have more cars having an automatic option, autonomous, I should say, that's the correct word to say. Automation will be up to 40% by 2050. And then that's also going to see an increase of miles driven because of the added effect of ride share fleets. So given these trends, a couple questions. What impact would a combination of the following have on air quality in 2050? You have the increased miles driven, you have more people, then on top of that, you have the cars, which will increase access, more miles driven, you have automation, you have the electric vehicles. And then will the changes in air quality from electrification of passenger car fleets be substantial, particularly when you compare it with a cleaner gasoline-powered car? And then what impact will climate have on air quality when you consider an electrified fleet scenario? So our objective is to evaluate the efficacy of electric cars, accounting for all those things. And like you can see, we also considered the representative concentration pathway 4.5, but we also considered 8.5 as well. And we try to quantify the differences towards clean gasoline-powered cars. I'm only going to present some of the results here for sake of time. But our overall approach was to start with the team at UT Austin, which is heavily in transportation modeling. Dr. Kokerman's group, they gave us a predicted car demographic in 2050. So we used this car demographic and we scaled up to determine from 2016 NEI, that's the emissions inventory, to get a projection of what 2050 emissions would be. And then we used moves to simulate what the emission would be for for certain pollutants. And then we use smoke, which is one of the modeling tools we use in CMAQ, and then eventually get a final CMAQ output. This is just an idea of moves. It's basically a MySQL database GUI. You can enter in all your car demographics, and then once you run the query and when you run it, you will get an idea of what emissions are coming out by car type, by road type, by year. You can get all the data from there, and then you use these as scale factors to scale up your emission inventory to 2050. This is just generally some CMAQ, the setup. We have to consider all these things when we do our setup. The emissions inventory is here, the meteorology setup is here, and then finally the air quality model is here. We did a 12 kilometer by 12 kilometer grid size. These models can run at 36 kilometers. That used to be what they used to be run at, but most people now run them at 12 kilometer by 12 kilometer. They can also go down to 4 kilometers too, but that increases the computational time. And sometimes you may not get added benefit by going down to 4 kilometer. I intend eventually to go down to 1 kilometer though for fine scale modeling. Oh, and because we're doing future climate scenario, we take into account long wave radiation. That takes into account the greenhouse gases under both RCP projections. And then we also considered the emissions of future sectors, because it's not just transportations that will change. You also have power plants. They're going to have different regulations. They're going to have different sources. You're going to have housings. They're going to have different inputs. Energy use, different emissions profiles. You also have agriculture. So we had to do our best estimate and guess what those emissions would look like and the scale and the demand would be. And those results are actually published in a paper by Dr. Shen. So just an idea of a scenario run. Basically, you have your base case 2016, then you look at the future. You're looking at two season months. You're looking at winter, which we call January, summer, July. 2050, these are projected emissions. We consider an energy mix, which is renewable or non-renewable. Basically, if the EGUs are going to be we call them electric generating units, but these are basically the power plants. And then the meteorology, both of these, and the fleet electrification. So there are a bunch of scenarios. And if you do the factorial analysis, 2 times 2 times 2 times 2, you could easily get into 48 cases. So we had to select which ones we would use. So part of the results I'm going to show is comparing a moderately electrified fleet with no automation. And I call this a BAU case because we do know the cars will be electric in the future, but we don't know if the autonomous impact. And we want to assess it using considering climate as well. These are just the basic various adoptions in the future that we looked at, but I'll discuss more as I go into the results. So the first set of results is NOx. Basically, we have the effect of meteorology. So I have both January and July, and these are the ranges. You can see they range from 0.03 to 109. These are just some hot spots. So you have to plot the scale like oil and gas units there. So that's what's responsible there. But overall, you can see that the NOx levels are pretty low, about 5. The scenario here is a moderately electrified fleet, no automation, so no dynamic ride sharing. And we're looking at a stringent energy policy, meaning like the regulations of all those sectors are very stringent, like the best case scenario to control emissions. And we also consider energy use from EV charging and of course the 2 seasonal months. So we keep this the same so we can contrast for each different pollutant. So what we do, because we're assessing the impact on climate, you see if you look at these two plots, they kind of look the same. So what you usually have to do, you have to subtract. So basically you have RCP 4.5 minus RCP 8.5. 8.5 is the more adverse climate scenario. Generally, the changes are very minuscule when it comes to NOx, especially under different climates. You can see that the change is ranges from about 1 part per billion to about -1. Of course, you have some hotspots there, like I said, those oil and gas units, but generally overall, the US, they're pretty low. And slight increases, like I said, most below 1.0. And then this is where I plot the difference. So you can see the probability distribution. So you can see that most of them fall under -1 to 1. Now, when we look at VOC, this is a volatile organic compounds. We're looking at both July here, for instance, and you can see we subtract 4.5, 8.5. We kind of see some trends that we did not expect. What we expected under the more warmer climate was that there would be higher degree of VOCs because you have trees and they will emit more biogenics. But however, what we ended up seeing was that you're going to see, so anything that's red, RCP 4.5 is higher than the 8.5. So basically, you're showing here that you have more volatile organic compounds under the 4.5 as opposed to 8.5. That was a little bit unexpected, but overall, there's generally lower volatile organic compounds. Winter is a little bit more what we expected in line. So this is just the patterns on the distribution of VOCs. Now we get into particulate matter. And so this is January, same thing. You could see a reduction in the east and maybe some slightly higher levels in the west coast and as well as upper north. And this is the range -21 to 16 generally, but you can see most of the range is about 5. But however, when you look at a seasonal month of the summer, you can see that there's more particulate matter, which we would expect because it's warmer, you have more secondary organic formation. And then, of course, once again, we see that there's the differences between 4.5 and 8.5, that it was higher particulate matter in 4.5, which we did not expect. And one of the explanations that are coming out of this is because when you're looking at climate, you really have to take an average of more than 1 year before you can make a really good, strong assessment on climate. Because this is just one climate scenario that is predicted. So what we would need to do is run the WRF model for like 5 years and then average it and then run our CMAQ inputs again to see if we get the same trend. So that's one of the explanations that we have. But the interesting thing is that what's contributing most to the particulate matter is biogenics. You can see this ranges up to 5 micrograms per meter cube, and this is 0.25 anthropogenic. So it's definitely been driven by the WRF, it's driven by the meteorology, and it's driven by the biogenics. So we have to understand that more. And then the last thing I'm going to, oh yes, please. Yes, isoprene. Yes, thank you for the clarification. Yep, exactly. And then so the last thing, 8-hour ozone. So this is where you can see, of course, you have higher ozone in the summer months. And in January, good news. Well, I don't know if it's good news, but this is what we expected to see. We expected to see less ozone in those winter months, and we expected to see less ozone under 4.5 RCP scenario. However, when you come to the summer months, the reverse is noted in the southeast. Now, if that explanation of the meteorology not being averaged over 5 years is not the case, then this is the impact of the climate in this scenario. It could be NOx limited, it could be VOC limited, it could be changing the reactions, the chemistry there. So that possibly could be one of the reasons why you have higher ozone in the southeast, despite a warmer climate, a less warmer climate with the RCP 4.5. So unexpected climate change given that RCP 8.5 is warmer. So last but not least, we're going to talk about automation and EV adoption effects. So basically, these are all the factorial analysis you could do. You can see you can easily run into, let me look at that, at least over 40, 50 runs of every combination of these factors. And the computational time is a lot. More importantly, the space is a lot. I still have to clean up my cluster account. So we try to analyze using interaction plot, effects and interaction plot. Basically, if you see across these two main effects, there's some synergistic interaction, but if they're separate, they just they don't have a joint effect, and you can assess each effect on its own without having to consider the other one in combination. So this is the various adoption scenarios, but rather than tell you, I will launch into the results. So over here you have BAU. Remember, the BAU had no dynamic ride sharing, and you contrast that with a 5%. Basically, it's a price drop in automation. So the more of the price drop you have, the more battery electric vehicles you have. So basically what you have is you have added miles driven, but you have more battery electric vehicles. And what you can see is that with the BAU case, it's lower ozone. This is because of the added extra miles with the dynamic ride sharing. You have more miles with the dynamic ride sharing, as well as, you have more miles and more vehicles on the road. So that's why if you consider dynamic ride sharing, you're going to have slightly elevated ozone, about about 2 parts per billion. You can see there's a range. This is if you consider with 10% adoption range, where you even have more battery cars, but in this case, you're having more battery cars. Now you can see that the ozone drops down. So if you're going to consider the, dynamic ride sharing, you should probably do a conversion to electric, fully battery electric vehicles, because you won't get as much of an increase in ozone for the added miles that are shared. So that is what this shows, is that this reflects the makeup of the two passenger car fleets, and this reflects the addition of the dynamic ride sharing miles. So and then if you take, I think I have just one more slide after this. If you look into just taking ozone and looking at the interaction plot, EGU production means like you're taking the electric cars, use the energy mix of the future. If you use EGU REN, it means electric cars are charged on renewable energy. The interesting thing is that if you look at the renewable energy, there's a decrease in ozone, which you would expect. So this is telling you, like, if you're going to look at the electric cars, you should consider attributing the marginal electricity used to renewable fuels. And then, but if you look at the policy, now keep in mind, this policy is not just the electric vehicles, it's the other sectors. There's a slight increase in ozone, but not much, but a slight increase. But it's a slight increase in ozone, which goes into the chemistry of the regions. The different regions have different chemistry. And this is overall the whole US. Last but not least, I think this is very interesting diagram. So this is with the 10%, this is 10 is a price reduction. This is 5% price reduction, and then this considers the dynamic ride sharing, but if you convert everything to battery electric vehicles. If you're going to consider dynamic ride sharing with automation, you might want to consider changing everything to a battery electric vehicle, because that shows that has the lowest impact on, the greatest reduction in ozone with electric cars. And this is the business as usual case. So this converts all the DRS cars into battery electric vehicles. And then once again, if you consider under different climates, it has the same impact under both climates. Under RCP 4.5, under RCP 8.5, you can see that converting to a fully battery electric vehicle fleet will have a noted decrease in ozone. So which would be, I guess, an optimization problem, and this will pose the best solution. So the conclusions are that regional effects need to be considered, and the more ozone and particulate matter under RCP 4.5 than 8.5, which we were not expecting to see. And then moving to all battery electric vehicles, not a combination of hybrid and other cars, seems to be important. And automation will add to pollution, because you need to consider that you have more cars on the road, more miles driven, and then you need to consider moving to BEVs to realize additional benefits. And the combination of policy and regulations can be complicated. And climate also adds to some complications. It's not as linear as we expected. And then with that, just want to highlight once again, now with the electric cars, you've got to consider everything. You've got to consider the climate, you've got to consider the policy, you've got to consider the technology, you've got to consider the land use. So this shows you how complicated the question of electric vehicles can be. And this is 2 more slides I lied, just to hold you guys there. But advantages of fine-scale urban modeling, you can see you can discern patterns of air pollution and you can get to understand your urban processes a lot better. And can you imagine if we do convert everything to electric cars, notwithstanding the life cycle analysis, notwithstanding the source of the materials, notwithstanding issues that come up in flooded zones where the electric cars have been flooded, you can change this map. Can you imagine like all the pollution gone, like magic? And then all of this could change as well. And you could really improve the outcomes for vulnerable populations in like a city of Atlanta. So with that, I just want to come back to the questions I asked before, and I just want to thank my collaborators and my thesis advisors and everybody here at Berkeley, Dr. Ivy as well, and these are my co-authors, soon to be published paper, we hope. But thank you, everybody. Yeah. Thank you. Thank you. Thank you. Mm-hmm. So any questions? Yeah. I kept to time on that one. Yeah, I hope I did. So what do you guys think about EVs? Oh, yeah, sorry. Yeah.
One question.
Yeah,
I appreciated your connecting the talk to transportation throughout and making sure that that was explicit. And I wanted to ask you for the first part, the acidity part.
Oh, yeah.
Thinking about the sources of particulate matter of PM 2.5.
Yeah.
Do they all have the same acidity? So if we're thinking about primary sources like the fires or farming dust or engine combustion or secondary sources, are they?
Secondary sources.
What is driving kind of the changes in acidity, and
Okay.
are there
And both of
differences
them.
in terms of the different sources?
That's a very interesting question that I hadn't really worked at. But in terms of the acidity, it's definitely driven by the SO2 and then the NOx. So anything that has those sources will have a level of degree of acidity. With wildfires, I don't believe any direct measurements of those particulates have been done to test the acidity, because for the most part, you have to capture them. And I don't think there's a lot of capturing that has been done. I mean, you know, when you have a wildfire, they don't really capture those particulates and do the speciation on those. And you need the speciation to test the acidity. So it would be interesting to know what the source is, but then you also have aged plumes. By the time they react in the atmosphere and you get them, there's SOA formation, and that they would have taken up maybe some sulfur and some NOx. So it might be really hard to separate them. What I really saw the differences in the separation came about with temperature and the contribution of mineral dust. That would elevate the pH. Anything that was in a coastal region, you had more NaCl, that would elevate the pH. Another thing that elevated the pH was thermodynamics. When you had a cold winter months, and then you had more nitrate formation, and then that switched the pH from a low regime to a high regime. Those are the two things I have seen that have had a marked effect on pH. In fact, there have even been studies that have been done talking about elevated ammonia emissions, because ammonia is a neutralizing agent for pH. Even with increased ammonia, just the acidity in the in the particulate matter is so low that it inhibits the amount of ammonia intake. So my guess is that, I mean, the particulate matter from the wildfires, being that they'll probably be aged, they would have some level of acidity to may not be as much, but they would have some level. Yeah. Yeah, no problem. Yeah. Yeah. I'll try to get the slide up. Yeah. Sorry, it doesn't show. Okay. Let me put it. Okay. And that was a precision. Oh, yes, please. Sorry. Yeah.
has brought us into this fix is that we have never paid enough attention to urban planning and family planning.
Do we, so the
We
question,
have we have all this problem on account that we failed to do some of these other things that
We
need
have-
to get done.
we have the problem that we failed to address, you're saying,
Yes.
with the cars?
Well, you know, when you have urban planning, you know, you have car problems. If you have a family planning, if you lack family planning, well, then there's other kinds of
Problem.
population issues.
So, that is, so are you asking like how does the impact of family planning and city planning affect election?
Well, if you don't pay any attention to it,
Yeah,
you
nobody's paying
have
attention.
all of these problems that you're talking about today.
Okay, yes. If nobody's paying attention to it, and we were just talking about that in a class previously, I think that's the important thing. I mean, I don't know anybody have any thoughts, but I think that's the important thing of doing this work is to make sure that this work gets translated in layman's terms so that policymakers will really put some good policy in place. Like you're talking about family planning, I think you talk about the global population and all that.
I live in Mountain View, California. We're finally
Doing
dealing
something.
with the quality of planning. You know, we want to get people living closer to where we work so we don't have a car problem.
Yeah. That is true. That is true. No, thank you very much for that commentary. It's about planning and city planning. I have a minor in city planning, by the way. But yeah, thank you. Yeah, thank you. Yeah.
How does this work?
I had a question,
oh,
just probably
sorry.
a silly one.
Okay. Oh, sorry. Yeah.
So I'm glad you have this slide up because I was going to ask you to
sure.
go to it. So you have the climate and the land use and and in your models that you just described, you have different climate scenarios. Like that's what 4.5 and 8.5 are, right?
Yeah. Yes, exactly.
So my question is, does your model capture the interaction between climate and land use? So for example, my understanding is that under some climate scenarios, something like 60% of the US will be flooded by 2050.
Oh.
So that would totally change the land use and obviously have impacts. So are you capturing that linkage between those two effects?
No, not in this modeling, but not in this modeling. And this is a limitation, But the change in land use, exactly. No, not at this time. But what we are capturing is the change in vegetation and the biogenics, that land use model, and that really mainly is affected with temperature, precipitation, and volatility, but not with a complete change in land use, not yet. Yeah, that food for thought. That's a good grant there question. Thank you. Yeah, you said you had a question.
Oh,
I'm sorry.
I have a question about the climate. So in your projections for the climate, you talked about the two climates, and I've got a little bit confused because
Yeah.
I saw you doing summer versus winter
Yes.
climates, but then I also wondered if you were also talking about different projections on what the climate might be doing, if cooling or getting hotter, do you know? So were you capturing both of those, or?
I was catching both
Okay, thank
because,
you.
yes, you're right. Because, the climate has a different impact in the winter versus the summer. So normally one would do a full year, if, for the whole year, and then take an average of the whole year. But we really just wanted to hone in on the seasonal impact with climate. So yes, you're right. And they each have their own different temperatures and differences and everything. Yeah. And for the most part, the winter trends behaved as we expected, but not the summer. So, yeah, which is a surprise. Yeah.
I'm going to take the prerogative and
Okay.
ask the last question.
Sure.
Just a detail on your last study.
Okay.
Where did you place the power generation? Where are the renewables or the nuclears, or maybe, I don't know what sources you were considering, but did you place them in space, or is
Very
this
good.
imported from somewhere?
No, no problem. We place them in specific places as determined by the platform. So they use spatial surrogates and they use GIS mapping to place these. I wish I had shown a plot where I could just show you all the EGUs. They'll light up this thing like a tree, but we did not change the location. All we just changed was the demand and the ramp up. Yes, because we can't project where the new plants would be, but we just changed the demand overall. Yeah. But yeah, the NEI platform by the EPA, they have the current EGUs located specifically, and we didn't have to change them. But that would be interesting to do, to see what that does to the profile.
Great. Well, thank you.
Yeah,
and
thank you.
Join me in thanking Dr. Lawal.
Thank you, everybody.
Thank you.
Oh,
For our
thank
appreciation.
you.
Thank
This
you for
is very
spending your time with
nice.
us and for telling us about your research.
Oh, thank you, everybody. Thank you so much. Thank you. This is great. Thank you.
Thank you everyone for coming.
Thank you.
Our
I didn't
next
expect a
seminar,
gift.
Helen, do you remember off the top of your head? Or Amanda?
Kevin Geringer.
Kevin, next Friday. Okay, see you then. Thank you.
Robotics.
Robotics.
Robotics.